We finish our discussion of the symmetric groups by talking about transpositions. A transposition is just a cycle of length 2. So you can think of it as just a means of swapping two objects. So one thing to notice is that any cycle at all, and therefore any permutation in Sn, can be written as a product of transpositions. Right? So if we take a cycle, like x1 through xr, we can write it, in fact, in several different ways as product of transpositions. So in this first way, you can see a pattern emerging in the product of transpositions. And let's see if it makes some sense, right? So in the cycle, we know that x1 is sent to x2. Right? X1 gets sent to x2. Let's see if that works in our product of transpositions. So in the rightmost transposition, we look for x1 and we don't find it. And so we continue leftward until we do find it. And in fact, we don't find it until this very first one, where we see that x1 gets sent to x2, just as we had expected. Now the cycle sends x2 to x3. Let's see if that works. Well, we start at the right, we look for x3, and we never, or x2, and we never see it until we get here, where we see that x2 is sent to x3, but then x3 never appears in as we move to the left, and therefore x2 is sent to x3. So it does appear that this product of transpositions is doing exactly what this cycle does. And you should check for yourself that this bottom product of transpositions does exactly what the cycle does. So, here we have several examples, specific examples, where we write some cycles as products of transpositions. And the main thing is that, any cycle, and therefore any member of Sn, can be written as a product of transpositions. But unlike the situation for disjoint cycles, products, decomposition of permutation into a product of transpositions is not unique. Right? For instance, here, you could write the identity permutation like this, or you could add on a couple of 1, 2s. That would be another way to write the identity permutation. So the factorization of permutations into products of transpositions isn't a unique factorization. However, it turns out that each permutation does have a well-defined parity that's dependent upon transpositions. So we say that a permutation is even if it can be written as a product of an even number of transpositions. Likewise, we say that a permutation is odd if it can be written as a product of an odd number of transpositions. So the first example we have here is for us to determine whether a few permutations are even and or odd. So E we already saw a moment ago, right? We can write as a product, 1, 2, 1, 2, right? And so E is certainly an even permutation. Now, you might be wondering, well, is it also an odd permutation? Maybe there's some crazy way to write the identity as a product of an odd number of transpositions. Well, maybe you should think about that and see if you can come up with anything. Okay, now we have this giant cycle, and remember that according to the last slide, we can write this as 1, 3, 3, 5, 5, 7, 7, 4, and finally 4, 2. and we count up the number of transpositions that's 1, 2, 3, 4, 5 transpositions. So this is an odd permutation. In general, if you have an R cycle, a cycle of length R, it can be written as a product of R minus 1 transpositions. So we know this is an odd permutation. Is it even? Well, again, maybe that's something for you to investigate. Okay, here we have a product of 2 cycles. Notice that this, we could go ahead and write these out as products of transpositions, but let's not do this here. We know that 1, 2, 7, that's a cycle of length 3, and therefore it can be written as a product of 2 transpositions. So this is even, and that's even. And it stands to reason that if you multiply 2 even permutations, you should get a third even permutation, because the number of transpositions would be an even number plus another even number. So this is even. Is it odd? Well, hard to say. So it turns out that there is no permutation that is both even and odd. And you might have discovered, if you've read this theorem and the proof in the book, that this can be a remarkably difficult theorem to prove. And in fact, its difficulty sort of depends on the tools that you have at your disposal. So here in this slide and the next, I'd like to sketch a proof of this theorem for you that is a bit different from the proof that's given in the book. And the proof that I want to sketch for you involves what are called group actions. So we say that a group acts on a set if for each element of the group and each element of the set, there's a unique sort of element that you get from those two that lives in the set. And this pairing satisfies the following properties. So the first is if you take the identity element and you apply it to some member of the set, you should just get that member of the set back again. And if you take 2 group members, multiply them together, and apply that product to an element in the set, that should be, you should get the same result as if you did this incrementally. That is, if you first applied G2 to your element of the set, took stock of what that was, and then applied G1. So here we're going to look at a specific group action. We're going to look at the group being our symmetric group, Sn, which is what we've been focusing on. And X now for us is going to be the set of n by n matrices with real entries. And this symmetric group, Sn, can act on this set of matrices X by permuting the rows of the matrix. That is, if you take a permutation in Sn and a matrix in our set X, then the permutation acts on that matrix by sending the ith row of M to the f of ith row of f dot M. So also, I want you to recall something from linear algebra, right? That if you take 2 matrices and you obtain one from the other by swapping 2 rows, then it has the effect of changing the sign of the determinant. Okay, so that was our setup for the theorem. And now let's go ahead and prove the theorem. So remember, the theorem says that there's no permutation that's both even and odd. That is, it's impossible to take any given permutation and write it both as an a product of an even number of transpositions and as a product of an odd number of transpositions. So let's start with a permutation in Sn, and we're going to let I, capital I sub n, be the identity n by n matrix. And we're going to argue by contradiction. So let's suppose that this f is both even and odd. Then that means that we can take f and we can write it as a product of an even number of transpositions, if we like. And we could take f and write it as a product of an odd number of transpositions. So now what we're going to do is we're going to let this f act on the n by n identity matrix according to the action that we talked about on the previous slide. That is, a permutation will act on a matrix by permuting its rows. So if I take the determinant of the new matrix I get by letting f act on the identity matrix, well, that's the same as the determinant of this matrix. And you see that to perform this action, we're letting these transpositions act successively on the identity matrix. Now, each time one of those things acts, there's a swap of rows. And we saw in the previous slide that a swap of rows induces a change in sign of the determinant. So since the determinant of the identity matrix is 1, if I want the determinant of this new matrix, all I'm doing is I'm changing sign, 2t times, which means I'm taking -1 to the 2t power, which gives me 1. Now the same thing, again, we can compute the determinant of f acting on the identity matrix, but this time we think about f as being represented or expressible as a product of an odd number of transpositions. And then using the same argument that we gave above, we can see then that that determinant really is -1 to the 2m plus 1, which is -1. -1 and 1 are not equal, and so that gives us our contradiction. And so we conclude that there can't be any permutation that's both even and odd. So we can use even permutations to define a class of important subgroups of the symmetric groups. So if we let A sub n just be the collection of even permutations in S sub n, then this A sub n is actually a subgroup of S sub n, and it has order n factorial over 2. So A sub n has a name. It's called the alternating group. Or maybe we would call it the alternating subgroup of Sn. Right, so we're going to go ahead and prove this theorem. So remember, if we want to show that a subset of a group is a subgroup, there are a couple of things we need to do. We need to first show that the operation is binary on An, and we need to show that anything in if you have something in An, then its inverse also lies in An. So first of all, the operation is binary on An because if you take two even permutations and you multiply them together, you get another even permutation. Now, suppose you take, some element f in the alternating group. Right, then it's an even permutation, which means it can be written as a product of an even number of transpositions. Now, if you want to know what F inverse is, you can get that just by simply reversing the order of these transpositions. Right? The reason for that is that if you take any transposition times itself, say x1 times x2, any transposition times itself is the identity, right? You're essentially swapping something and then swapping it back. Okay, so the inverse of this f can be obtained just by reversing the order of the transpositions. And if we just simply reverse the order, that doesn't change the fact that there are an even number of them, and so f inverse also lies in A sub n. So this alternating object is in fact a subgroup of the symmetric group. And then the question is, well, what about the order of the alternating group? So you can define a function from Sm2 itself, sort of a multiplicative function where you take f and you're just going to multiply it on the left by the transpose 1, 2. So it turns out that this function, it carries a sub n bijectively onto the set of odd permutations. And so if you want to know what n factorial is, well, we already know it's the order of the symmetric group. And the symmetric group we saw a moment ago in our previous theorem, it's the disjoint union of the even permutations and the odd permutations. But the odd permutations and the even permutations have the same size, right? So this is essentially just 2 times the size of the even permutations. And so if you divide by 2, you wind up with the thing that you want, that the order of the alternating group is n factorial over 2. So we finish this video by looking at some specific alternating groups, namely A3 and A4. And we're going to determine the elements of these groups. So we begin with A3. And before we start writing down elements, maybe it's good to know how many elements to expect. On the previous slide, we learned that the size of A3 should be the size of S3, which is 3 factorial divided by 2. So that's 3 elements. So we know to expect 3 elements. One of them is going to be the identity. And it turns out that the others come from the 3 cycles in S3. So what are those? Well, we've got 1 going to 2 going to 3 and back to 1 again, which can be written like this. So that's a product of an even number of transpositions. And then, well, what's the other 3 cycle? Well, it's the inverse of this one, namely 1, 3, 2. And that can be written as 1, 3 times 3, 2. Or if you wanted to use the method of the previous slide, you just take this original cycle, 1, 2, 3, look at its product of transpositions, and then just reverse that product. So that would be 2, 3, 1, 2. So either way you choose to write it, it's an even number of transpositions. So the elements of A3 are the identity and the 2, 3 cycles, each of which is the inverse of the other. Okay, now A4 is a little bit more tedious to deal with. So there, how many elements do we expect? Well, we expect the number of things in S4, which is 4 factorial, divided by 2, which means that we expect 12 elements in A4. So one of them is going to be the identity. Now, why don't we do what we did in A3 and go looking around at some cycles? So 4 cycles aren't going to do us any good because remember that 4 cycles are written as a product of 3 transpositions and 3 is odd. So the 4 cycles are bad. So why don't we look at some 3 cycles instead? So we have to be careful to make sure we get them all. So we could take 1, 2, 3. That's a perfectly good 3 cycle, which is an even permutation. And we could take its inverse, 1, 3, 2. And then we could take 1, 2, 4. And its inverse, 1, 4, 2. And 1, 3, 4. And its inverse, 1, 4, 3. And then 2, 3, 4. And its inverse, 2, 4, 3. And then, we might decide that we've run out of 3 cycles. So now we're going to look at products of disjoint transpositions. Like how about 1, 2 times 3, 4. And then maybe 1, 3 times 2, 4. And then 1, 4 times 2, 3. And at this point, I'm having trouble coming up with any more, and so now we count and see what we've got. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and luckily we know that we're expecting 12 elements, and so we know that we're done. So this collection here is the subgroup A4.